In this video, which begins Unit 4 in AP Chemistry, we're going to talk about changes in matter. This whole unit is about the changes that occur in matter in detail later on, but we're just going to begin by talking about two basic categories, the coarsest sort you can make of changes in matter by identifying and contrasting chemical change versus physical change. A chemical change is when bonds are broken and formed to rearrange particles. And by particles here, we really mean atoms. So matter is being rearranged at the atomic level to form new compounds or to isolate elements as chemical change takes place. Here's a good example. Hydrogen and oxygen can be used to make water. So the first step in that process would have to be breaking up the hydrogen molecule and the oxygen molecule. Then the next step is water forms from hydrogen and oxygen. So this is a rearrangement where two hydrogens are attached to one oxygen to make a water. What we start with is called reactants, and what we end with in chemical change is called products. We know that atoms can't be created or destroyed, so balance is needed here. So we can't do this with just one hydrogen molecule and one oxygen molecule. Instead, we need two hydrogen molecules, and when we break those up, we now have enough hydrogen atoms to make two water molecules. A chemical equation is very common in chemistry, and it's a symbolic representation of this reaction. And rather than drawing this all out in particles, we can have a kind of a shorthand. So how we do that is we write the formulas for the reactants, and then we put what's called a coefficient out in front that represents how many of that particular reactant we have. So the 2 means we have 2 molecules of H2, and the lack of a coefficient on O2 implies that there's 1 needed. And then we write an arrow that represents the change, and on the other side we would put down H2O because that's what we have, and then 2 because we have 2 of them. Now this is for 2 molecules or 2 atoms. That's what the coefficients represent, or 1 molecule, 1 atom, whatever it is. But it also refers to moles, so you can use those to reference mole quantities of reactants and products as well. Let's look at another example. What would be the equation for the formation of NH3 from N2 and H2? So NH3 is going to involve 1 nitrogen and 3 hydrogens. Clearly, we don't have enough hydrogens to do this, so we would have to think about another hydrogen molecule to provide us with that 3rd hydrogen in NH3. But that's going to leave us a leftover hydrogen, and it's going to leave us also a leftover nitrogen. So we can start making another ammonia, but we would need more hydrogen. So a 3rd hydrogen molecule would be broken up, and that would give us the remaining 2 hydrogens we would need to make a second ammonia. So the balanced chemical equation would be N2 with no coefficient, because there's just 1, plus 3 H2, because we needed 3 hydrogen molecules, makes 2 NH3. A physical change, by contrast, we're not breaking and forming chemical bonds. Instead, we're just breaking and forming IMFs to rearrange the particles. So an example of that would be melting ice. In solid ice, hydrogen bonds hold the water molecules together in this space-filling structure that we've seen before. And then after melting, the ice has been given enough energy that those bonds are overcome, and then the particles can move close to each other and then begin to move around in the liquid state. Before, we had water. After the change, we still had water. All we did was we broke up the intermolecular forces, the hydrogen bonds and dipole-dipole interactions that were holding them into that structure. Another example of a physical change would be dissolving something. So, for example, ammonia, which is normally a gas, can be dissolved in liquid water. Before, we have water and we have ammonia, and afterwards we have water and ammonia. They're just physically organized in a different space, and that required breaking up the hydrogen bonds between the waters to make enough space between the waters for the ammonia molecules to fit in there. No chemical bonds are broken. We just broke some IMFs to make this physical change happen. So we had the same substance before and after. We've seen these differences at the particle level. How can we tell the difference between physical and chemical change at the macroscopic level, at the level we can actually visualize with human eyes. Well, one evidence that we can see that chemical change took place is a color change. If there's a color change that is unexplained in any other way, like we're seeing in this video, that would be evidence that a chemical change took place. There were actually rearrangements of atoms. So that's one indicator. Color change is an indicator of a chemical reaction. If you see that happening and there's no other valid explanation for it that you can think of, well, it's probably chemical change. Another evidence that a new substance is forming is the formation of a solid precipitate. So here we see two clear liquids being mixed together and this solid yellow precipitate forms. When there's no other explanation for it, the formation of a solid in two liquids, that's a precipitate, that's evidence of a chemical change. Another one is the formation of a gas. And again, if you were like boiling water, there's an explanation for the water bubbles that you see of vapor. But if there is no other explanation, not an obvious explanation, like we have here where this penny is mixed with this clear liquid and it forms bubbles, and those bubbles appear to be making a brownish colored gas, that's evidence that a chemical change was taking place between the copper in the penny and whatever that liquid was. Another evidence of a chemical change is the disappearance of a solid. This video shows a piece of sodium being put in water. And this piece of sodium lights on fire actually, and it's zipping around the surface of the liquid. And now the solid is gone. Now it didn't dissolve in the water like sugar or salt or something like that would. We didn't see just a gradual disappearance of that solid that's otherwise explained. This is a chemical change that was taking place. Another evidence that a new substance formed is a smell that didn't exist before, that is unexplained. So mix two things together and suddenly you start to smell something that you didn't smell before. Probably that's because a new substance was created, a new compound that wasn't there before, and so you couldn't detect it. And then energy is absorbed and released during chemical change. And again, this is unexplained absorption or release of energy. So we know it's going to take energy to boil water, and that's a physical change, or to melt water, for example. That's a physical change. That's a change in the phase energy of substances. Changes in chemical energy are unexplained by any other means. Like, for example, when we looked at that sodium being dropped in water. The sodium lit on fire. There was a kind of an explosion, a rapid release of energy. That was not explainable by any physical change. Something must have been going on between the water and the sodium that released all that energy. So remember, energy can be absorbed or released in three modes. Heating, we would experience that by a temperature change. Radiation, we would usually see that as light, some kind of emission of light. And then also working. This is less common in chemistry, but an explosion or an expansion of a gas inside of an adjustable volume chamber would be places where we would see working being evidence of energy being released. Last topic for this video is talking about the two different categories of properties that we will see in substances. One type of property is called an extensive property. And the word comes from the fact that these depend on the extent of the sample. A good example of that would be mass. A large sample of the same substance would have a bigger mass than a small sample of the same substance. Volume. Volume is literally the extent of the space that's taken up. Heat capacity. How much capacity a piece of matter has to absorb energy without changing temperature is its heat capacity. So if you have two samples of identical substance, like for example, a bucket of water from Lake Superior and all of Lake Superior has a much greater capacity to absorb energy through heating without temperature change than the one small bucket. It depends on the extent of how much stuff you have. Another one would be energy. A forest fire, for example, releases way more energy than a burning match, even though the forest might be made of pine and the match might also be made of pine. So it depends on the extent Those are extensive properties. There's another category of properties called intensive properties, and they don't depend on the extent of the sample. It doesn't matter if you have a big or a small sample, you're going to have the same value. A good example of that would be density. A small sample of aluminum and a huge sample of aluminum, they're going to have very different masses, but their density is going to be the same. They would have very different volumes too, but density is a ratio of mass to volume, and that is going to be constant. It does not depend on how big the sample is. Specific heat capacity is the capacity of a certain quantity of a substance to absorb energy. So, for example, in our Lake Superior versus bucket of Lake Superior water, both of them have the same specific heat capacity because it's for every gram or for every mole of water or for every liter of water. It's a ratio that does not depend on the extent of the sample. Temperature is another one. Going back to the forest fire versus match, the forest fire and the match will have the same temperature if they're the same substances burning, no matter the extent of the total amount of energy released through heating, which is extensive. So temperature is an intensive property.